Hello everyone, my name is Ustav Matviyev and today I want to present you our researchment about a CUDA-based algorithm for Lidar position determination in mobile robotics. So let's start with the problem statement. Autonomous localization and environment perception are essential for a mobile robot to perform high-level tasks. As for robot localization, odometry and inertial sensors cannot avoid the problem of error accumulation. Therefore, exteroceptive sensors must be used to achieve effective localization and mapping. Among various external sensors, two-dimensional laser sensors can provide accurate and reliable environmental information with a wide viewing angle. They are widely used in perceptual tasks, including localization, mapping, and place recognition. The problem of determining the lidar position with optimal accuracy and in an acceptable time is relevant in various fields of application. Examples include smart house, vehicle route planning, dynamic map construction, collision avoidance, atmospheric research, cartography, economic efficiency management, and etc. As known, the particle filter algorithm solves the problem above. However, the number of reading iterations after each movement is significant if the lidar moves many times in space. Accordingly, the execution time of this algorithm increases several times. That is, it is impossible to decide in real time. One of the options for solving this problem is the development of a parallel algorithm and its optimization using CUDA technology and the graphics processors of the NVIDIA video card. So, our purpose of this study is to optimize the LiDAR localization algorithm using CUDA technologies. The object of research is an algorithm particle feeder for LiDAR localization, and the subject of research is CUDA technologies for parallelization of algorithmic code. Nowadays, various issues of robotics are inclusively researched. There are many articles that talk about different ways to improve localization using GPS sensors and various cameras. There are articles comparing different technologies using such as MPI, OpenMP, OpenCL, and CUDA. There is also an article that discusses the parallelization of the algorithm based on OpenMP technologies. OpenMP parallel computing technology is used to optimize the computing process in order to accelerate it and provide real-time results. As a result, the author managed to speed up the computational process by about 8 times and achieve an efficiency of 0.97. After conducting a detailed analysis of the problem considered in our work, it was noted that no one has optimized the particle filter algorithm using CUDA technologies. So let's consider the algorithm in more detail. Lidar successfully performs two actions. First, it scans the space around itself, and second, moves in space by the vector with some margin of error. It is also important whether the initial position of the lidar is specified. If so, then we can fill the array of particles with coordinates of that position, but if not, then we need to generate a certain number, which we set, of particles that will be placed randomly in our premises. This is done using ray tracing algorithm. The idea of the algorithm is to count the number of intersections of the room walls with a ray emitted from a point horizontally to the right. If their number is even, then the point does not lie in the space. But the point is suitable if the intersection number is odd. You can see it on the figure. So, first we set the coordinates of the verticals of our room. After that, depending on whether the initial position is specified, we fill the array with random particles or particles with the initial position coordinates. The next step will be a LiDAR scan of the surrounding space. You can see it on the figure. The scan takes place k times, starting the movement horizontally and to the right, and each measurement differs from the previous one by an angle that changes by 360 divided by k degrees. This way we get an array with the distances from the lidar to the room's walls with a given ray launch angle. The next we calculate the weights for each particle. The calculations is as follows. First, take the first particle from the array. Second, calculate the angle relative to the horizontal, the final coordinate of the end of the segment, which starts in the particle coordinates and has the ray length from the array. You can see it on this formula. Calculate the perpendicular length lowered from the end of the segment to the nearest room wall. Add the square of the length of the perpendicular to the temporary variable. Then repeat steps 2 to 4 for each ray in the array. The next, the weight of the particle is calculated according to the normal distribution formula, which you can see on your screens. And then repeat steps from 1 to 6 for each particle. The next step is to repopulate the particles based on their weights. The procedure is divided in 4 stages. The first stage is to add up all the values of particle weights. The second stage is to fill the new array of weights with values equal to this formula, where S is the sum of all values. Thus, we normalize them so that their sum is equal to 1. The third stage is to fill in an array that has a value like this. In this way, we will get an array of weight intervals. The fourth stage is generation of random value from 0 to 1. Then we need to determine which rank in the weight array the number belongs to. The index of that range would correspond to the particle that should be created. The complexity of the algorithm described above can be calculated as like this, where n is the number of Lidar movement iteration, k is the number of measurements at every step, r is the number of the walls in the room, and q is the number of generated particles. As a result, it grows very rapidly. One of the methods of optimizing this algorithm can be the parallelization of certain particles. For the most part, the most time is spent on the calculation of weights and repopulation, so these stages of the algorithm are parallelized. Thus, the complexity of the algorithm should be significantly reduced. To reduce the implementation time and increase the algorithm's efficiency, we will compare the algorithm execution time to a different number of processor threads using OpenMP technology, and we will also make the time measurements of the graphic processor using CUDA technologies. So, for CUDA technologies, sum-based calculation function is defined as global, which indicates that this code passage will be performed on the graphics processor. Additionally, calcwaits method will cause auxiliary functions which will be defined as a device. It means that only a graphics processor can cause and perform such functions. Numerous experiments are conducted on a graphic cards with 4 multiprocessor blocks that can perform 512 threads. That functions for determining the block size is CUDA occupancy max potential block size, which is a heuristic manner calculates the block size that reaches maximum occupancy. The threads group is called the CUDA block. Each CUDA block is performed by one multiprocessor and cannot be transferred to another multiprocessor in GPU. One multiprocessor can perform several simultaneous CUDA blocks depending on the resources required by CUDA blocks. Each core is performed on one device, and CUDA supports several cores on one device at a time. In this way, we call calcwait function, passing grid size and block size as parameters. Here, block size is the number of threads on the block determined by the CUDA occupancy max potential block size function. Grid size is the number of blocks we calculate by the formula, like this, where n is the size of an array. In our case, it is the number of particles we will generate. So, this section will feature tables and figures showing the program's time, speed, and efficiency with the different numbers of threads. The input was taken from the algo tester. Here is sample of input data, where we can see at the first row number of walls, then their coordinates. At the next row, the two numbers. First is the number of movement of Lidar, second is number of measurements on each step. Next, 3 numbers standard deviations. Then we can see that our initial position is given and coordinates are 1 and 1. And then we can see measurements of Lidar and vector on which Lidar has moved. The program was tested for 4 different input variations with varying root shapes, the number of walls, iterations of Lidar, and the number of measurements at every step. 3000 is the number of particles, which was selected for the most accurate localization. So, Table 1 presents the execution time of a sequential and proposed parallel algorithm based on OpenMP technology in a variation of the threads number 2, 4, and 8, and the values obtained by the acceleration and efficiency of our parallelization without this distribution between threads. K and M are the input data described above. TS is the time of performing a sequential algorithm. TP1 is the time of execution of the parallel algorithm based on OpenMP technology. S is acceleration, and E is efficiency. Analyzing the results of the first table, we see that when performing an algorithm with 2 threads, acceleration was obtained close to 2, and efficiency also goes to 1. Since numerous experiments were conducted on a 4-core processor, we have received reliable results. Acceleration with 4 threads was approximately 3.5 and efficiency 0.89. When using 8 threads, it was possible to improve the acceleration and bring it closer to 5.6. However, the efficiency decreased significantly and was 0.7. All this is because the number of threads in the last 2 causes exceeds the number of cores in the multi-core computer system. The results can be significantly improved by choosing computers with more cores. Still, the results obtained should have the same trend between the number of cores and the variation of the threads number. On the table 2 are presented the same result on the basis of CUDA technology and the graphics processor. Here, TP2 is the time of the parallel algorithm based on CUDA technology. In table 2, acceleration is close to 20, and it is known that when using CUDA technology, the performance is not calculated. Therefore, the proposed parallel algorithm has improved about 4 times the acceleration based on CUDA technology compared to OpenMP technology. The result of table 1 and table 2 for visual analysis are presented on figure 1. On figure 2 is presented acceleration, and on figure 3 is presented efficiency obtained based on OpenMP technology for different number of threads, 2, 4, and 8, and based on CUDA technology. So, we propose and investigate the parallel algorithm for determining the current Lidar position using CUDA technologies. The result of using OpenMP technology are also compared. As a result, it was possible to speed up the process about twice times and achieve an efficiency of 0.99. The algorithm is accelerated almost 4 times and an efficiency of 0.98 was obtained. The acceleration was reached approximately 19.8 by using CUDA technology for parallel algorithm, but the results can be achieved in the future based on the proposed parallel algorithm using more powerful computing system. On figure is presented the configuration of the computer on which the numerical experiments were performed. Here you can see some references which we used in our researchment, and that's all. Thank you for your attention, and if you have any questions, please contact on this email.